Welcome to my video course on engineering FRMCS. Today we're diving into something absolutely crucial. We're going to look systematically at how to configure gNodeB and UPF nodes to map wireless 5QIs over to backhaul IP network DSCP values. Mapping things like 5QI65 to EF or 5QI69 to CS5. As our railway networks make that massive leap to modern 5G architectures, making sure mission-critical data is prioritized properly, literally from end to end, is just paramount. So we're going to see exactly how we bridge that gap between the cellular wireless domain and the fixed IP transport network.
So here's a quick look at the agenda for today. We'll start with number 1, QoS in the FRMCs. Then 2, the DSCP mapping requirement. 3, architectural solution. And finally 4, standardized mapping values. All right, let's jump right into section 1, QoS in the FRMCs.
Okay, so within the 5G domain, quality of service is governed by the 5QI, the 5G QoS identifier. You can think of 5QI as this, well, it's like a standardized parameter that basically bundles up specific latency, priority, and packet reliability requirements for a distinct QoS flow. To make sure critical railway applications like, remote driving, automated train operations, or emergency voice communications, to ensure they function flawlessly, the whole system relies completely on this 5QI. It guarantees that the air interface allocates the exact right amount of resources, giving us strict packet delay budgets and those incredibly low packet error rates over the wireless link between the train and the cell tower.
Moving on to Section 2, the DSCP mapping requirement. Now, while 5QI handles the wireless side perfectly, we hit a bit of a wall, a fundamental engineering gap, really, when that data leaves the immediate 5G core. Because, let's face it, a railway communication system isn't just made of cell towers, right? Since the traffic flow to endpoints, like a trackside gateway or your central control server, has to traverse an external IP or MPLS backbone, we run into a translation issue. Those standard backbone routers, they simply don't understand 5QIs. They literally don't speak 5G. Instead, they operate on the IP layer, and they need DSCP traffic classes, differentiated services code point values, which sit right there in the IP packet header to prioritize packets correctly as they route them across the fixed network. Without this crucial mapping step, a mission-critical train control packet would be treated exactly the same as some routine background diagnostic update. And we definitely do not want that.
Section 3, architectural solution. So, how exactly do we get the 5G world and the IP backbone world to seamlessly cooperate? Well, if you look at the architecture, the key players are the gNodeB in the RAN and the UPF in the core. These are the actual physical nodes where QoS enforcement and packet mapping rules are applied based on your overarching network policies. Now, the session management function, or SMF, that acts as the brain here. Actually, scratch that. It's more like the chief dispatcher, pushing down the rules. But the heavy lifting of actually inspecting the packets and tagging them, that happens at the network edges. The gNodeB sits at the edge of the radio network, and the UPF sits at the edge between the 5G core and the external IP data network.
And it's important to note that the mapping process here is strictly directional. It depends entirely on which way the data is moving. For uplink traffic, meaning data traveling from the train up to the network, the gNodeB is the one responsible for taking that incoming wireless data, reading its 5QI, and then mapping it to the appropriate DSCP value before it sends it off into the transport network. On the flip side, for downlink traffic, so data going from the network control center down to the train, the session management function actually provides configuration rules to the UPF. The UPF then physically marks that downlink IP traffic with the correct transport DSCP values on a per QoS flow basis before it travels back through the transport network toward the radio tower.
All right, Section 4, standardized mapping values.
So now that we understand the directional flow and the architectural nodes that actually do the work, let's look at the concrete application tables you're going to need when provisioning these nodes. First off, we have to associate the specific railway application with its mandatory 5QI, because obviously not all railway data is created equal. For instance, standard, routine data, maybe a non-urgent diagnostic log, that gets assigned a default 5QI of 8. But highly critical communications, like an urgent driver-to-controller voice transmission, those demand a much stricter prioritization profile to ensure zero latency and zero drops. So urgent voice gets assigned the mission-critical 5QI of 65. The network literally has to be engineered to respect these distinct application categories.
Consequently, when you're in there configuring the gNodeB for the uplink or the UPF for the downlink, These specific 5G values have to map directly into the IP world using standardized DSCP codes. As we touched on earlier, 5QI65, that's our urgent voice traffic, absolutely must translate to EF, which is expedited forwarding. EF is the highest priority standard traffic class, guaranteeing immediate forwarding with minimal delay across all those IP routers. Meanwhile, 5QI69 maps to CS5, class Selector 5, which is a high-priority tier we often use for critical signaling. And finally, our standard 5QI8 simply maps over to the default traffic class, which basically means it gets best effort delivery whenever the network is busy. This strict one-to-one mapping is exactly what guarantees that end-to-end performance.
To summarize everything we've covered today, mastering this directional mapping at the gNodeB and the UPF is absolutely critical to the safe operation of modern automated rail networks. You're bridging that massive gap between wireless 5G precision and fixed IP routing. As an engineer, you always have to ask yourself, what happens to a mission-critical emergency brake command if a single router drops a mislabeled packet just because it wasn't tagged with expedited forwarding? Well, the seamless translation from 5QI to DSCP ensures that never happens. Thanks. We can see you next video.